Hi, welcome to Teardown Tuesday. Bit of vintage test gear yet again, and it's a Fluke beauty. One of the original Fluke Scopemeter portable oscilloscopes. Vintage because it's 1996 or thereabouts, but geez, you know, it seems just like yesterday, 96, you got to be kidding me, but that was 17 odd years ago, so this thing is pretty ancient. You know, comparatively speaking. So this is the Series 2, so there was a Series 1 before this. Is a 50 megahertz Fluke 91 Scopemeter. Here it is, scored it on eBay for about 50 bucks. Bargain. It was advertised as not working, but unfortunately it does actually appear to work. So I was hoping to get a repair video for this thing. Once again, been foiled. Unbelievable. But anyway, should be really interesting to crack this thing open, have a look inside a 17-year-old portable Scopemeter. Let's go. And here it is compared to a Fluke 87.5, which is not a small multimeter in its own right. So you can see how huge this beast actually is. Absolutely enormous. It's probably not as heavy as you'd expect actually, but geez, it is absolutely enormous. I got some probes with it. These weren't advertised. Basically multimeter probes and oscilloscope probes as well. This is only the one channel model, which we'll take a look at. Unfortunately, look, check out one of the leads. It's been, look at that, chopped. Bummer. And it is the Fluke 91 Scopemeter Series 2, 50 megahertz analog bandwidth. Sample rate? Well, I'm actually not sure. It doesn't tell you the sample rate in the manual. This was back in the day when, well, they thought, people are a bit scared. They don't understand this sample rate stuff. They want these things to look and work exactly like a real scope. So, we won't bother telling you that. But so it doesn't actually list in the manual on the specs what the sample rate for this thing is, but based on the glitch capture of 40 nanoseconds, you know, I think it's presumably that's the sample rate. It's got to be at least 25 megahertz or something like that. So it's not a real-time scope as such, in that the sample rate is not, you know, at least 4 or 5 times the input bandwidth, for example. But you know, menu-based interface. The screen, it looks huge, but it's only 240 by 240 monochrome. No, it's color garbage. And of course, it's got multimeter and scope functionality as well. And if you have a look at the top here, let's flip that around. You can see that this is only a single channel model. I didn't actually know they came in a single channel model, but apparently they do. There you go. And it's got regular scope inputs as well. And you can apparently, and a generator output as well. It can generate signals as well, and it's actually Cat3 rated, which isn't too bad at all. And apparently you can use the common terminal in combination. If you've got the dual inputs like this, you can actually use the common terminal in combination with the dual channels if you want to, or something to that effect. So anyway, it should be interesting inside this thing to see what sort of technology it'll be. Mostly predominantly surface mount, or mostly almost all surface mount, of course, but probably not integrated in one large chipset. So there's probably going to be quite a bit inside this thing, or most likely separate multimeter and oscilloscope boards as well. That'd be my guess. But yeah, let's crack it open. It comes with this rubber boot, of course, and on the back here I've taken off the battery cover on the back. Let's have a look in here. There we go. UL listed. Fluke Scopemeter 9444. There you go. Is that a date code? Maybe? I thought it was 96 or thereabouts. But check it out, folks. Made in Holland. All my viewers from Holland. Beautiful. There does seem to be some corrosion down on the contacts down here, and that's why it was sold as not working, because the guy who sold it apparently you know, whacked some C-size batteries in it, and it didn't work, so he just sold it as is. Now, as you can see, rather curiously, you can see that it's got an extra tab down here. This is for the rechargeable battery pack, so you can put in 4 regular non-rechargeable C cells, and of course if it doesn't detect using that tab, then it won't attempt to charge those. So you can use two different types of packs there, and also a 12. You'll notice these two here mark 12 volts and 0 here. That's for another pack which goes in, which isn't a battery pack, but that connects to a 12 volt power source, like an automotive power source or something like that. And on the side here we've got a really deep DC input jack and an opto isolated interface as well, just a infrared transmitter and receiver via serial, I'm sure. So yes, although this is a 50 megahertz analog bandwidth scope, its single shot bandwidth is going to be pretty poor. Unfortunately, its response is probably going to, update rate's going to be very poor as well, I'm sure. And the sample memory, whoa, hold on to your hat, folks, 512 bytes. Yep, bytes. And that's the optional high-res mode, 512 samples. Normally it's only 256 samples, but you can punch a turbo button and double that. Woohoo! So let's crack this thing open, and we can actually get in here with a flathead, believe it or not. And looks like this panel, this end piece, is going to lift off, and that, and then there's only two other screws by the looks of it. So that should, oh, yep, there we go, bingo. Oh, look, we've got little rubber surrounds on there to keep the dust and moisture and crap out. And yeah, there's definitely, the other one is certainly not fitted under there. So there we go, that's coming apart already. So it looks like, oh, by the way, it's only got one screw. It only came with one screw down here. So maybe somebody's had a hack at it or something like that. But I have powered it up, and it does actually work. So there we go, it's apart. It looks like it's going to flop open with a ribbon cable. Here we go. Ta-da! Hey, look at that. Oh, beautiful. Alright, what we've got here, beautifully laid out in two halves. As you can see, all of the processing and display stuff all on this side, connected via, you know, a 25-way ribbon cable or something like that over to the main power supply part, as you can see, with all the caps and all the battery management stuff. And looks like under here we've got all the shielded scope and multimeter front ends. So that it'll be interesting to see. I'm assuming that, say, maybe the analog to digital converter is under here, and then it's just getting the data back over to the processor side, because there's no other connections. There's no, you know, high frequency or coax connections from one side to the other. So I don't think they're actually you know, outputting analog stuff on this ribbon cable. So I can only presume that the ADC and capture side and the multimeter front end is all under there. So I'll crack that open. We expect to see more under there, but let's have a look at the processor side. One of the first things I noticed is that they're interestingly divided this. You can see it on the silk screen, divided it into a grid base pattern, and, you know, I, H, G, 1, 2, 3, 4, and that's for servicing, cross-reference and stuff like that. You know, the component is located in, you know, I4 or something like that. So, you know, I don't think it's needed on a product of this size, but I guess that was Fluke's, you know, internal policy and way of doing things. So the designers just followed that. And I can see a bit of that on the other board as well, which we'll take a look at. But I always see as a couple of custom Fluke chipsets. We'll take a closer look in here. There's another Intel device over here which we'll look at, but it is nicely modular design. Like the battery sense circuit is around here. There's a receiver / battery sense circuit. There's external RAM contrast circuit around here, and they have labeled them and grouped them quite nicely. I like it. And we have 6 Hitachi LCD dot matrix driver chipsets there, all surface mount, pretty basic stuff. They've decided to integrate this onto the main board instead of having that separately. You know, there's a bit more engineering work in that. You could have divided it up. Really, you could have divided your workload up and said, right, we're going to put all the display stuff on one board or something like that. But no, they decided, oh, bugger it, we'll just integrate it on a single board, go for broke, and you know, it's obviously going to be cheaper to assemble and test and stuff like that, and when it's all on the one board. But yeah, they're the design trade-offs when you're starting a design like this. Well, do we make it, you know, a modular board for the LCD display and associated circuitry, and then have a ribbon going over and stuff like that, and then you can divvy it up, test them all separately, qualify them all separately, and you know, stuff like that. So there's pros and cons both ways. I guess in the end it really comes down to your company's particular methods, or an individual design team's methods and things like that, and what they're trying to achieve. And we found the date code, folks, 9423 on most of these chips, around 94. So yeah, that serial number on the back of, or that date code on the back of the unit was actually correct. Almost 20 years old, this sucker. So the manual said 1996, so I guess the manual was last updated in 1996, but actually manufactured in 94 sometime. Now, bingo, we've found the main processor. Here it is, an Intel S83C196, part of the MCS 96 family of processors. This one's got 8K ROM built in, and goes back, copyright 1986. Brilliant. Made in Japan, back when they made the bloody things in Japan. Now, if we take a look at the layout on this thing, here's this custom Fluke chip over here. It's the Fluke, well, it's got Fluke MASIC on it. I have no idea what that stands for at all, but clearly if you look at the memory interface on this, I mean, this thing's capable of, you know, it has external memory interface, but it seems, and here are the three, and here's the all the flash over here, the program ROM. So really that seems tied into the Fluke ASIC down here. So, and then that, so it looks like it's some sort of memory controller or something, you know, some sort of ASIC that does memory control or something like that. And it's also connected to the keyboard as well. You'll find that goes over to the front panel keyboard. So really that's like a keyboard and memory interface controller, perhaps, something like that, with Intel processor running a maximum of 16 megahertz, by the way, this thing. And well, we got a 74HC 132 there, a couple of other miscellaneous, got a resistor network happening around here, but this main LSI, there it is. It's another Fluke ASIC. It even says it's an ASIC on there. And, well, yeah, I don't know how you go about getting info on that. You probably can't. Fluke proprietary. So, yeah, that's running at 25 megahertz. So, you know, you've got to wonder what that's doing. It's got some memory interface to it here. So we've got a known 16-bit processor down here. Not a bad 16-bit processor for its day, really. Kind of what you'd expect to find in a product of this vintage. And then we've got the two ASICs, custom Fluke ASICs, around here, and they're both interfaced to memory. This one's interfaced to external SRAM up here, so and also down to this flash down here. So you know, it's almost as if based on its location to the display driver up here, kind of like that is probably some sort of display processor or something like that. That would be my guess anyway. And then this one down here is just an external memory and keyboard controller for this processor. So it's like the processor is maybe, you know, when they were designing this thing, this is an oscilloscope, you know, it's got to process a lot of information, do a lot of stuff, update the screen in, you know, as fast as it can, all that sort of thing. We can't really do that in a processor of this day, really. So we're going to have to do a custom, let's roll our own custom ASIC up here to do all the heavy duty display processing and stuff like that, perhaps, and another one down here to offload you know, some other tasks or something like that, keyboard and memory controller, maybe a direct ADC to memory controller or something like that. So maybe the data's coming directly in from the ADC side of things, and this ASIC not being processed by the, not being handled by the processor, but maybe being dumped straight to sample memory or something like that. Yeah, definitely controlling the display, because you can see the traces snaking their way around here like this, going over to the display driver chips around here, and of course they're all interconnected. So that is the best guess, that handles all of the graphics processing, and maybe you know, taking the samples and directly displaying it, so the processor is not responsible for the update rate and stuff like that. It's all handled by the ASIC. Oh, how cute. We've got an LM324 and an old 4093 quad Schmidt NAND gate. Classic. And that looks like it's somehow, that's like the RAM power. That's what it's got there. So I don't know, maybe what's it doing? Is it, you know, your guess is as good as mine. I don't know. But if we lift this board out of here, let's have a look on the bottom. Yeah, I didn't expect to see anything on the bottom at all, and sure enough we don't. We just get some test pads down there. You can see the manufacturing test pads down in there. All those gold contacts, so that contacts there, little gold pads, so that would have gone down onto a bed of nails production tester, and possibly used to program all the flash memories once they're in circuit and stuff like that. And looks like we just have a bit of a shielded grid down here, pattern on the bottom of the membrane down there, and yep, there you go. Nothing special, but yeah, they've decided to do that as a mesh based one instead of a solid ground. And down here we've got our soft latch on-off power circuit, which would be continuously monitoring the on-off membrane switch on the front panel. Now let's take a look at what's going on the battery side of things here, and we've got some serious capacitance happening around here. Looks like we might have a big inductor or a common mode choke or something like that in there. Looks like there is a common mode choke there for our DC power in, and underneath this little shielded can I see two inductors down in there. They're actually identical looking inductors to these things here. They don't look like inductors, but they've just got tape on the outside of that, but there you can see the windings on the ferrite core there. So yeah, we've got a decent amount of switch mode stuff happening there. These would be low ESR caps, presumably top quality. What are they? Let's have a look. Does it say, what is that? A sexy brand capacitor. Well, they are very sexy. SXE. And it turns out that's not actually the brand, that's the type, and they're from Nippon Chemico. Absolute top quality, as you'd expect. And of course I missed that. That's the Nippon Chemico symbol down in there, and the SXE is the series model of the capacitor, and these are high temperature, low ESR caps, as I suspected. And we have ourselves a current sense resistor, folks. There it is, 0.1 ohms, 5%. That's in series with the battery pack down there. And I can't quite see the Murata part number down in there, but it's a Murata part, and it looks like we've got 4 ferrite beads there with a filter cap. So if you look at the DaveCAD drawing here, it just looks like that in series with the DC input jack. And if we get this shield off and look under the skirt, there it is. Hey, nothing under there, not much at all. But once again, we've got that silkscreen component grid happening, which tells you where the parts are. There must be more stuff on the bottom down in there. We've got a couple of relays up there. We'll take a good close look at that, but looks like that board's going to have to come out to see the goodness on the bottom. Now on these portable scopes, if you haven't seen them before, you might think this is just a fancy red painted BNC, you know, just a regular BNC painted red, and you might think, well, how can it make electrical contact when it's got that red paint on there? Well, check this out, folks. It bends. Not sure if you can see that. I'll get in there with the screwdriver. There we go. It's flexible. It's not metal, folks. It's plastic. And if you have a look deep down inside, you can see the real metal is somewhat inset right back down in that connector, and that is of course for safety, because you don't want to be you don't want to be able to touch any of the grounded part of the circuitry, because the idea of these handheld meters is that they can take floating measurements, so you don't want the idiot user to be able to touch them. There you go, that's a better view of how deep inside the real shield part of that BNC connector is. So while that looks like a BNC connector, smells like a BNC connector, it ain't one, folks. So you can't just go and use a regular scope probe on that and think you're going to get it to work. And yeah, it's just got the regular outputs here. There's the center conductor, there's the ground. Incidentally, the ground is this capacitor wrapped tightly around that lovely, beautiful, look at that, someone's gone to a lot of trouble there, beautiful work, and has soldered that onto the ground connector, and that's AC coupling the ground, or the negative input on that BNC through to presumably signal common and the internal shielding. And let's see if that's circuit ground. So we'll go between the shield over here, and well, let's go between the common terminal, the negative terminal up here of the multimeter, and yep, that's actually connected through to the negative terminal. Okay, so the ground, circuit ground, and let's just take this choke here. We can, no, doesn't like that. Other side, yeah, there we go. It's connected through to the negative of the DC input jack and the negative of the rest of the circuit here. But of course the negative on the BNC over here is not, it's AC coupled through to there and doesn't directly connect. As you can see, it's only, it's 515 ohms, and I believe there's an option in the software to either ground that input or not via one of the relays there. So that's all, that depends on the measurement configuration that you're actually trying to do. And on the multimeter side, of course, there's not much happening there at all. There's a couple of relays in there. That one I think might be the one I just mentioned, switching the ground in. But we've got a MOV there. We've got a high voltage cap and a resistor, through-hole resistor, and well, that's about it. There's not much on the top of this thing at all. Boring is the proverbial batshit. And here we go. I took the two screws in here out, and I do like the design of this. Very minimalist in terms of screws. So absolutely chock-a-block. Look at that. And look at that. It's a thing of beauty. A real steel plate. Oh, love it. And we have got a fair amount going on this board. Here's our analog front end up here, which we'll take a look at in a bit more detail. The unpopulated, well, almost unpopulated. The chips are certainly there to duplicate that second channel, but the BNC's not there, and the relays and other stuff on the top side of the board aren't populated in there to do the second channel. So it's partially there, so I'm not sure what's going on there. And we've got our ADC up here, which I recognise. We'll get onto that. Got some power stuff happening over here, and some looks like we've got some quad analog switches happening, 7.4 4000 series CMOS type stuff, and another mysterious chip in here. Let's take a look. The largest device on here, I don't quite know what that is. I tried Googling that. No, nothing turned up at first pass, so I'm going to have another crack at that one. It's a Philips, yeah, like OQ0308T 34004ME. I don't know. If I find anything, I'll annotate this later. Then we've got some 74HC stuff for the data. And here's an old friend, the Philips TDA8703. And I instantly recognise this because I've used this chip before in my own digital storage oscilloscope design, the DSOA Mark III, way back. So a year or two after this, I think I did that in about 95 or thereabouts. I think it was published in 97. Or something like that in Electronics Australia magazine. Anyway, use the TDA8703. It's a flash 8-bit analog to digital converter, primarily designed for video type applications, but you could certainly use it for an oscilloscope, and I did, and it looks like Fluke have as well. But you'll notice that it's only got a single ADC. There is no second one. And it's a pretty basic flash, 8-bit flash converter, really. It needs like external voltage references and stuff, external level shifters and all sorts of things, to make the thing work. But, it's not bad. It's 40 meg samples per second maximum, so that's the upper sample rate of this thing. Obviously, I'm not sure if it does actually get to 40, but curiously, I believe the minus 3 dB input frequency range of this thing only extends to just under 20 megahertz. So it's puzzling how they're getting a 50 megahertz bandwidth using this converter. So what's actually going on with this ADC? I'm not sure, because it's minus 3 dB bandwidth is only 20 megahertz, yet this is a 50 megahertz analog bandwidth scope. So, you know, somewhere there needs to be an ADC capable of handling that. So I can only presume that the only way they're doing it is some sort of sample and hold circuitry around here, maybe, you know, based on this analog switch here that is sampling, and then, which is obviously sample and holding the value, and then it's being converted at a slower rate by the ADC when it's not in real-time mode, i.e. when it's doing equivalent time sampling, which is sampling at a slower sample rate than Nyquist. So really, I think that's what must be happening there. Otherwise, I can't see how they're getting that minus 3 dB 50 megahertz bandwidth on this thing. Go figure. Anyway, there's definitely only the one ADC there being used to sample both channels, unless this particular device is another ADC, which is sampling at, which has a higher bandwidth or something like that. I don't know. We need to find out what that sucker is. If anyone's got the schematic for this thing or the service manual, please let us know in the comments or on the EEVblog forum. And we've got a 74HC 4316. That's a quad analog switch, and there's quite a few of those placed around the board in various locations. So lots of analog switching, and that's what's they're using the same one over on the analog front end over here as well. So it looks like we've got our analog. It looks like we've got our input amp there. We'll take a look at that, plus all the analog switching for the range stuff, I presume. And our input amplifier is a National Semiconductor LF453. No surprises there whatsoever. That's a BiFET input, high-speed precision op-amp, designed, you know, almost ideally suited to an application like a ADC or a scope front end in this sort of class. And you'll notice down in here that they've cut a couple of isolation slots there and there, and those components which are bridging them like that are actually ceramic caps down in there. There they are, 4 of them there, 3 of them there. So they're isolating the signals between the input section over here and the rest of the part of the measurement circuitry. And here we have a 27 MCAC. It's actually a TLC, a Texas Instruments TLC 27 M2AC, and that's a precision amplifier. They've got one sort of there in the middle of the board, then they've got another one. Curiously, I thought this was a matching LF453 to up here, but it's not. On channel 2 down here, they haven't got the matching device down there. It's that TLC device. So I don't know what's going on. We certainly don't have a true channel 1, channel 2 mirrored circuit configuration here. And incidentally, you'll notice the largest solder pads on these outer pins of all of these chips, and they're solder thieves. They go under various names, but this is designed to be wave soldered, and you can tell this board has been wave soldered instead of reflow soldered. You know, if you look over some of the power stuff over here, it's clearly, you know, had the molten wave just go right over this thing. And the idea of these, so obviously all the components need to be glued down for that to take place, and then these just ensure that you don't get solder dags happening between pads. You just get, as the solder wave goes over this thing, you actually get a larger pad on the end, allows you to capture any excess solder that's coming off like that. And there's a Signetics SG3524D pulse width modulation power controller. So that's just you know, powering some DC to DC converter stuff around here, and LM285 1.2 volt voltage reference. And of course, there's one thing you'll notice lacking around the multimeter inputs or anywhere on this board is your traditional Fluke multimeter type functionality. It doesn't have that Fluke input custom switching chip and all that sort of stuff. So they're just using the regular scope ADC here for the multimeter functionality. They're just switching it in on a different channel, and that's pretty much it. And you can see the result of that in the specs. The specs for the multimeter on this are pretty darn ordinary. But that's pretty much all she wrote for the analog and multimeter part of the circuit. I don't know. I was expecting something a bit better than that. Just a 8703 ADC, shared between the channels if it has the dual channels, and still don't know what that one is. But yeah, there's not much happening there. It's all just data, the 8-bit data output and the clocks and things just coming from the processor board through that ribbon, and that's all she wrote. A few little trim pots around here just to compensate they're not even near the input dividers, so they're not, and not for compensating the input divider, but they looks like they're somewhere near, like compensating this high voltage isolation part of this here. So they're doing a few tweaks there. There's some diode protection going on there for the multimeter stuff, I'm presuming, and there's an amplifier for the multimeter, and pretty ordinary. And they really have minimised the number of screws on this thing. Look, they've got their attention to detail. They've put the little PCB catches, like holder spaces integrated on the battery compartment there. So the board sits under there. So we've got spaces under there which hold it in place. And you only need the 2 screws, or the 4 here, but it keeps all this front panel stuff in place. Really is quite elegant. Alright, I'll probably get lynched if I don't power this beastie up. So I've got it hooked up to my bench supply up there. So let's switch this sucker on. Beep. Woohoo! And we're straight on. There we go. Now, one of the real problems with this is that the screen is just totally washed out. I'm not sure what technology they were using back then. It may not even be, STN or something like that. I'm not sure, but it definitely, I'm pretty sure it's faded. Because if this was its original contrast, then, well, it's not that great at all, and we can change the contrast like that. It reminds me of like the old TDS 210 scopes kind of thing, that, that really washed out, very low contrast look on it. So, I don't know if anyone remembers using these back in the day, but I'm sure that they do age. It's pretty horrible. Anyway, there's our waveform. We can actually move it around, and we can feed signals into it, and it does actually work. It's as slow as a wet week. Absolutely terrible. The menu system is absolutely atrocious. We've got the Scopemeter. We can actually change it to meter mode like this, and it actually displays our waveform plus our multimeter up the top here. That's not too bad at all. That works reasonably well. And then we've got ohms mode. There it is. Whoop-de-doo. We've got diode mode and external millivolts. Yeah, I think. So, it's not that great of a multimeter really in terms of specs. They've just added it in as a bonus. I mean, the combined multimeter. And the multimeter, by the way, has got a 5 megahertz bandwidth. So it's pretty good, actually, in terms of what a meter is capable of in terms of bandwidth. So that's one of the awesome aspects of using the 8-bit ADC. But then, the multimeter, well, it's only using a crappy 8-bit ADC. It's not that good. Actually, come to think of it, that's probably what that other chip on the board was that I couldn't quite get the number for. Maybe it's another higher resolution ADC just for the DMM part of it. Not entirely sure. So anyway, what we have here, folks, is let's say we're in scope mode, then we can get into sub-menus, and then we've got to use the menu keys to, hang on, how do we, no, more scope, and then we can jump around in here, and there's our capture length. We can set that to 10 or 20 divisions. Glitch detect, 40 nanosecond glitch detect, that's okay. And whether or not you want average in, whether or not you want persistence and stuff like that. So you've got to use that, and then you've got to go select item, and then you've got to scroll down again, and you can get infinite, and you can change the width of the trace, and you can do all sorts of stuff. But yeah, really convoluted sort of menu operation for this sort of thing. It's pretty retarded. I mean, we do have dedicated range keys down here, so as you can see, it goes down to 10 millivolts per division with a times 10 probe there, all the way up to 5 volts per 10 volts, 20 volts per division, 50 volts per 100 volts per division, 200 volts per division, 500, a kilovolt per division with a 10-to-1 probe. And the time base goes down to 10 nanoseconds per division in equivalent time sampling mode. Of course, it's not a real-time sampling scope below, I think, 100 nanoseconds per division. But of course, obviously, you're only going to get that 1 kilovolt per division with the optional high voltage probe for this thing. And I actually got 3 of these PM8918 10-to-1 scope probes with it. Really quite neat. One of them, as you saw, had a big cut in it. But let's see if we can feed in a signal here, see what we get. Alright, I'm feeding in a 1 kilohertz 5 volt peak-to-peak sine wave. So let's press the dreaded auto set button, shall we? You can hear the relays going click, 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 click. And yeah, there we go. There's our, can I move it? I can move it up if I hold down the button. There's overshoot on the wave, like it sort of, you have to be very delicate. You can't hold down the move button, but you can see at 1 volt per division there, it is bang on. 5 divisions, awesome. And then if we go down here to user options and go into meter mode, it should pop up with our waveform, which is off the screen there. Hasn't scaled that correctly, and it can't measure it, presumably because it's off the screen. And there we go, I just ranged it down a bit, and we're getting 1.75 volts RMS AC. That's at 1 kilohertz. Let's up the frequency and see what we get. And there we go, there's the same waveform again at 4 megahertz, because as I said, in meter mode it's only got a bandwidth of 5 megahertz. So let's put that up to 5, see if we can measure that. Yeah, it can. Let's go up to 6, see if we can still measure that. No, overload. But there's our 6 megahertz sine wave there, so let's bump that up to say 25 megahertz, shall we, and see what we get. And there's our 25 megahertz sine wave at 10 nanoseconds per division, and let's drop the time base right down, and we'll probably see some aliasing here as we drop down. Yeah, you can see it's going to start to do it. Here we go. There we go. Drop the time base down. Yeah, there we go. It looks perfect, doesn't it? You would think, aha, look at that perfect sine wave at 50 microseconds per division. Wah. Nope, that's aliasing. And there's a 10 megahertz square wave. It's not handling that too bad at all given the bandwidth. So yeah, this thing isn't exactly a user-friendly modern scope, that's for sure, but it is, you know, a early 90s and 94 vintage, almost 20-year-old oscilloscope technology here in a handheld form factor, and incredibly useful for its day, especially with the 50 megahertz bandwidth and, you know, the basic multimeter functionality and stuff like that. Very popular little units these Fluke Scopemeters were. So if you've got any further info on these, service manuals, stuff like that, I'm sure everyone would love to see them. So please post them in the comments or jump on over to the EEVblog forum when you can discuss this ancient stuff. I love it. Vintage test gear. Vintage. Oh, 1994? Are you kidding? Vintage? Unbelievable. Anyway, if you like Teardown Tuesday, please give it a big thumbs up. Catch you next time. Hi, welcome to Teardown Tuesday. It's another bit of vintage test gear, and it's a Fluke. Woohoo! One of the first handheld multimeters. Multimeter. It's a bloody oscilloscope.